afternoon, everyone. Or not everyone. Where the heck is everyone?
There's a job fair.
I think there's a job fair, yeah.
Oh, yeah.
All right. Well, good luck to everyone. It's a job fair then. So, today, any questions before I get going? So today we're going to talk about context-free grammars, which are a way of defining what are the valid strings in a programming language. So imagine that we're defining a new language. Some programmer writes their first program in that language. Then we want to translate that program into executable code. The first thing we need to do is analyze to make sure that that program is free of errors, or if it does have errors, to show the programmer where those errors are. So we need to what's called parse the program. There's a convenient way of specifying which constructs are legal and which ones are not in a programming language by giving a grammar. It's kind of like an English grammar, but of course more formalized and more rigid. So we're going to be using what's called a context-free grammar. So each language, and really each subpart of the language, can be defined by these grammar rules. In a context-free grammar, you have you specify rules, and let me do it backwards from what's written up in the slide, or as they're called, productions. A production has on the left-hand side what's called a non-terminal, because it's something that does not occur in the actual language. It's a construct that we that we use to define the structure. So here we have a non-terminal symbol called term that ultimately we want to reduce to something that does occur in the language, or a terminal symbol. So a terminal symbol is a token in the language, such as in Java, class, or 3.14, or plus. So here we're saying that if that a term can be reduced to, or can be rewritten as, a factor times a term. So this happens to be a recursive rule. And you can have more than one rule for the same non-terminal. You can say also a term can be written as a factor. So term and factor are concepts that I came up with, or that people have come up with years ago for these kind of arithmetic expressions. And these are the rules that govern what they are. So let's see what we can do with these two rules. So one of the things that I can do with term is I can say, okay, a term is, by using rule number one, a factor times a term. Then I can take the red term here, and I can further decompose it and say that the red term is also a factor times a term. And I keep the factor times before. And now I can rewrite the red term by using the second rule and say the red term is a factor. So now I have established the fact that a term can be reduced to factor times factor times factor. Of course, now I also need to figure out how do I further reduce factor, because factor is still a non-terminal, so it's not something that can be a part of the language. And we'll see in the next slide how to do this. So that's the basic idea of context-free grammars. The context-free grammar is a set of productions, these rules with a colon, equal, and then one keeps running those productions until one has derived a string that only contains terminals, and that's then a string in the language. When you do that process, you can think of it as building up a tree called the parse tree. So in this particular example, we started out with a term. We used the first rule, that's the first row of arrows, to say that a term is a factor times a term. So that's this row of bubbles under term. We then used the first rule again, but this time on the rightmost term, to say that particular non-terminal then gets blown up into three non-terminals. And then we used the second rule on the rightmost term again now to reduce that to a factor. So now we got this tree out of there that describes how we did this derivation. That's a useful tree. It's important to remember that, useful as it may be, it is different from the expression trees that you saw on Monday. They both have their value. They both look like trees, but then it's different trees. So what a parser does, it's a software component that carries out this derivation process according to some grammar. And as it does that carrying out, it does some actions. And there are two kinds of actions that it could do. One of them is it could compute the value of this of an expression, for example, and you would have that in an interpreter. Or it can produce code. And actually, it's difficult to produce code right away. What's typically done is that the parsing builds up an expression tree, that other kind of tree, and then later in code generation, the expression tree gets translated into code. So the job of the parser is to build up some intermediate data structure in a convenient form that can be used ultimately to generate code. So we're going to have to write these parsers. Given a grammar, we need to write a program that then can read a string and produce these actions. We'll see in a minute how to do that. But before doing that, let's look at another example for grammars so that you get a feel for what is involved in writing a grammar for something simple. So I want to be able to generate lists of integers where adjacent integers are separated by commas. And so here I'm giving you a plausible way of doing it. I'm going to say a list, that's the thing that I want to drive, has quotation marks, sorry, not quotation marks, parentheses, has parentheses, and then it has some contents in between, where contents is something that I have to define. It's another non-terminal. Now what could contents be? Looking at the third example, the contents could be nothing. Looking at the first example, the contents could be a number. Looking at the second example, the contents could be a number and a comma and more contents. It's recursive. These rules often are recursive because how else? The only way to produce an arbitrary sequence is to reuse recursion at some point. So that set of rules seems plausible, but it's wrong because it can generate not only correct strings but also wrong ones. Let me show you how. So I could derive the string 1, 24, enclosed in parentheses using these rules. Because I could say a list is parentheses with contents inside, and then using the third rule for contents, I could say the contents inside is the 1 comma followed by more contents. Again, using the third rule, that's 24 comma followed by more contents, and then using the first rule for contents, I could then say, and nothing more, and I have a valid derivation of an invalid result. So I'm going to have to trash these grammar rules. They're not good for what I want to produce. Here is a similar looking set of grammar rules that actually works. So here I'm again saying that a list is parentheses with contents, and then I say contents could be a number, or contents could be a number followed by contents like before. But now I'm handling the case of an empty list differently. I'm saying up here that a list could be an empty list. So I'm not saying that contents could ever be empty. Yes?
These are based on the number of arguments. And to figure out which one is linked to.
I'm sorry?
So how the top and I don't know how they are connect together, or they are count by the number of arguments.
These four rules make up the grammar of my language. They're not connected together in any particular way. I came up with them. So I claim, and I didn't prove it, I claim that these four rules will produce lists of integers in the format that I envision, parentheses on the ends, and then comma-separated integers in the middle. And I came up with them. There's no recipe for it. I've designed other grammars, and this is the grammar that produces it. And so let's again go slowly and see why this works. So if you have an empty list, clearly the first rule produces it. If you have a non-empty list that has a single number in it, then using the first rule of list and this first rule for number is going to give me that. If I have more than one number in the list, then I can use the first rule here, which gets me this number, and then followed by more contents, which inductively is going to then also work. Now, the grammar rules that you've just seen were written in what's called BNF, or Backus-Naur form, by the inventors of this device. So these guys came up with this rule for this way of making grammars. Interestingly enough, for Algol 60, a programming language that's now older than all of us. So Algol 60 was really the first high-level programming language that was designed with programming language design in mind. There were a couple of predecessors, such as Fortran, but they kind of organically grew. And with Algol 60, a bunch of people came together and said, we want to design a programming language. We want to be explicit about what is valid in this programming language, what is valid syntax, what is the semantics of it. And so they did an amazing job, and so Algol 60 had a huge influence on programming languages after, so much so that famous computer scientist Tony Hoare said that Algol 60 was an improvement not only over its predecessors, but also over most of its successors. And so when you look at some abominations such as C, you can really see that. So it would have been nice if more languages had followed the footsteps of the Algol family of languages. Anyway, so the original BNF notation is what I've just shown you. You have productions, and that's all you have. But it turns out it's nice to have a few extra conveniences in it. And that's sometimes called extended BNF notation. And it really is the same thing that we have with regular expressions, where the purists say this regular expressions, there's only 3 forms, but it's nice to have some extra convenient syntax. So here's the convenient syntax that we want. That we want to allow on the right-hand side of a production alternatives. And you could write 2 separate productions, but it's a little more convenient. We want to allow repetitions. And in the literature, there are 2 kinds of ways that people often write repetitions. You could either use an asterisk, like we use for regular expressions, and some people use a curly brace to say 0 or more. I'm going to use the first one because it seems more in tune of what we're doing. For 1 or more, people write a plus symbol, just like with regular expressions. And for 0 or 1, you can write a question mark, like with regular expressions, and you'll see elsewhere some people put a square bracket around it to say that this thing is optional. Like sometimes when you get the syntax for a Unix command, you may see those square brackets for optional. But we'll stick with the ones that look more like regular expressions. So with that, oops, I should have put a colon equal here instead of the equal. We could write a grammar for the list from the previous slide by saying a list is an opening brace followed by this thing here, which that's optional. And what is it? It's a number followed by this thing that's repeated 0 or more times.
Do you have to escape parentheses?
Well, here's the thing. We have to, because now in the extended BNF, where we have syntactical marks, we have like the asterisk, the plus, the question mark, and then you have to use parentheses to group them. In that case, we do need to have a difference between the parentheses in the eBNF notation and the parentheses as they are parsed. So I will be careful, I hope, to always put double quotes around the things that are terminal symbols. I realized I was not careful about that a couple of slides back, and I should fix that. And as we come to doing this thing in Scala, that'll come automatically. So now the thing is, we're going to be writing these grammars for simple programming languages. And people write grammars for complex programming languages. When you look at the Java language specification, which you can download, that gives in hundreds of pages the exact syntax and semantics of Java, there is a grammar in there that extends over dozens of pages. Someone has figured out a grammar for C++, and so you can actually write parsers that parse Java and C++ and process those in some way. You might not want to write a compiler, but you might want to do something else with the Java or C++ code for whatever reason. So you can write these parsers, and you could write them by hand. You could write something where you figure out how to follow each of the grammar rules. And that part is very tedious, and people don't usually do that. Instead, one tries to generate these parsers automatically. So again, a parser is a program that reads in another program, a program in a different programming language, and that carries out actions whenever a new part of the program, according to the grammar, has been discovered. And so there are parser generators that will eat a grammar and produce a program that reads programs. The most common parser generator that you might run into if you have to ever do something like that is called Antler. It's a very nice system. It also has an IDE with it. It's an open source project that actually happens to be run by a fellow who lives next door, almost next door to me in San Francisco. And so he and his collaborators have been perfecting this thing over the years. If you ever need to professionally do this, Antler should probably be the first thing to look at. There is a much more ancient thing that you may see once in a while called YAC, which is an acronym for Run for the Hills. It does the same thing in C, and it is really hard to use, and it's probably outdated at this point. And there's others. There's a thing called Java CC that I've sometimes used that's kind of simpler than Antler, but really Antler is the go-to tool for that if you need to do this professionally. We are not going to do this professionally. We're going to be using a library that's built into Scala called the Combinator Parser Library that is so incredibly simple that it's hard to believe in a way. So I'll explain the Combinator Parser with a very simple example. What you see in this slide is where it says class simple language parser. That is a parser that defines a set of functions that can be used to parse arithmetic expressions. We're extending the thing called Java token parsers that does the basic heavy lifting of how parsers work, and it gives a few functions that are useful for tokenizing Java, such as the function whole number that you see down here. Whole number is a function that consumes a whole number, an integer, according to the rules of Java. So let's look at what this thing does. It gives me three functions, the functions expr, term, and factor. Expr will parse or consume an arithmetic expression that's made out of plus, minus, times, and slash, the four basic arithmetic operations, and parentheses that may be necessary for precedence. So that's the job of expr. What it will return is an instance of the generic class parser, and inside the brackets is the type of what we are parsing. Later on, we will want to get it to produce a parser of some data type that describes expressions, such as the class that we had in the lab on Monday. But we won't be able to get to that today. We'll get to that next Monday. For right now, it's going to return something, and I'm just going to say any to describe that something. You'll see in a minute what it is. So it returns a parser of whatever. That parser data structure is basically there to tell us whether the parsing was successful or not. If it was successful, then we get the parsed whatever it is that the parser function produces inside. In this case, it's any. Later, it'll be an expression or a number or whatever, by calling get on it. On the other hand, most parsing fails, as you know from your own experience. more often than not, the programs that you run have some kind of syntax error. And in that case, the parser object gives some information of where the first error occurred. So parser is a wrapper over either I was happy, and then I can call get to get it, or it was unhappy, and then there's some methods where I can find out what went wrong. All right, so let's look at what the expr function does. The expr function is defined in terms of a term function, which you see comes further down. So term is a function. And then there's this thing called squiggle. And squiggle is followed by an opt, and then there's more stuff inside the opt. So what squiggle does, it says, first try this, and then try the thing that comes after it. So we're first going to call term. And so let's hold that thought and assume that term parses whatever a term is. After term has returned what it says is a term, then this expr function keeps on going, and it keeps on looking and says, oh, there's something else that optionally might be there. So what is that thing? This thing here is another parser that I'm not even giving a name. I'm just writing it down as a literal. This parser here is, again, a parser with a plus and minus, then a squiggle, and then it recursively calls expression. Expression is a function. You can call it recursively. So the parser here with the plus or the minus is has a string here. When a string is used, that is automatically converted to a function that consumes that string. So plus in this context means a function that eats the string and returns it. So we're having a parser that is willing to eat a plus or a minus. The or will try the one on the left, and if that one doesn't work, it'll try the one on the right. So what we're consuming here is a term, whatever that may be, we'll come to that, followed by a plus or minus in another expression. That expression is another recursive call, and so recursively you could also parse a term followed by plus and minus and something, and another plus or minus. I shouldn't say something. A plus or minus followed by a term, followed by a plus or minus, and another expression. So now we need to figure out what's a term. A term is just like an expression, except it calls factor for the left hand, and then it consumes multiplication and division, and then more terms. So what it really is, it is a bunch of factors joined with star and slash. What's a factor? A factor can be one of two things. It's a whole number. The whole number parser will parse numbers like 42 or 9 or whatever. It's a whole number, or it is a parentheses pair with an expression in the middle. That's how you get nested parentheses. So let's try one of those. So I will just try to parse like 3 plus 4 times 5. Actually, let me put this. And so we're starting out with expr, which calls term. It has to call term. There's no other choice. And nothing else inside here can consume the pluses and minuses. And so whatever term does is not going to consume this plus. We'll see in a minute what term does. And so that means this part is going to kick in. And so the plus is going to be consumed. And then we have a second expr that will consume the rest. Let's quickly see what this term does. Term calls factor. Factor calls whole number, which calls. Then this expr here will again call term. Now there's no more pluses and minuses, so that's all it can do. The term here we'll call factor. Consume the star, and then this factor we'll call whole number. On the right-hand side, we have term calling term again, which calls factor. Which calls whole number. So let me just be low tech and take a photo of this. So that's how the parsing process works. And I'll put the diagram here out on Piazza, and you'll just have to try that with some of your own examples to see how that goes. I've tried to explain it in the last section, and it wasn't any good. You just have to try it yourself. It's not really hard to do, but you can see that if you try to parse it any other way, it's just not going to work. Now, like I said, all of these, I should explain, why are they called combinator parser? So these parsers are called combinators because we can combine parsers out of trivial ones. So there's a few trivial ones, such as whole number and the ones that are marked by a string. Those just consume a single token. Then when you combine two of them by squiggle, then you get a parser that first calls the first and then the other. It's a combination of the two. If you combine them with vertical bar, then it's an alternative. It tries both ways. And finally, when you have an opt here, then that again takes a parser and it tries to apply it, and if it didn't work, then it just didn't work. So that's the combinations that you can do. Yes?
How does it know like what order to parse them?
It doesn't. It tries them all.
Oh, really?
Yes, until it finds success. So that's why these combinator parsers can be inefficient. If you have a grammar that's inefficient, and we're going to build some that are like that, parsing may not succeed because of that. And so you have to know a little bit to write the grammars in the right way that there aren't too many possibilities.
Okay.
So that's why for professional parser generation you wouldn't use this, but it's really great for quick and dirty. Yes?
So what exactly is opt? Is it a function?
What opt is?
Yeah.
It truly is a function.
Okay.
It is a function that consumes a parser and yields a parser.
Okay.
So that's why these are parser combinators, right?
Okay.
The various things that you see, squiggle and opt and the vertical bar, they're all functions.
This might sound like a totally like off topic, but maybe it's totally on topic. I'm not sure. Where do monads come into play here?
Not here.
Not here. Okay.
Not here. Although I'm sure I could come up with
Okay.
with a monadic interpretation of
I know
this.
there's an option monad, and that's like.
Oh yeah, well there is that, but that's
This is something else. Okay.
yeah, yes, something else. If we have an extra day, we can
All right.
certainly go into that rabbit hole. Yes.
Could you explain one more time what the squiggle means?
Yeah, the squiggle means first this, then that.
Okay.
So like here, we're first reading a term and then reading something else. And it's easiest to see it here. Yes, this first call this parser, which has only one mission in life, to find the left parenthesis. Then call expr recursive from here, and then find the right parenthesis.
Okay.
So in case the parentheses were not matched, suppose the right parenthesis was missing, then the thing with the two squiggles would fail because you could not do. So it would first parse the left parenthesis, then it would parse expr, and then if this one fails, then the whole thing fails. So squiggle means all of the ones that are squiggled together have to succeed. So when we write it in BNF, we don't write the squiggles. We just say we want a parenthesis, we want an expression, we want another parenthesis. But to put them together with the Scala combinator parsers, you have to explicitly put the squiggle for having that sequencing. Like I said, a parser is a function, and all parsers return something. When you have a quoted string in a combinator parser, it is converted into a function that consumes that string and returns it. So the return value is a string. When you have an opt of a parser, then it returns something of the data type option that we see in the next slide, that indicates something that's present or not. If you're familiar with the optional type in Java 8, it's exactly like that. And if not, I'll explain in the next one. Rep is a little easier to understand. Rep returns a list of the results of the parser inside. So you always use that when you want to have a sequence of something. You say rep of some other parser. The individual parsers, each of them returns something. Rep bundles them all together in a list. When you have the sequencing P squiggle Q, P will give some result, Q will give some result, and then we get an instance of the class squiggle. Squiggle is a valid class name in Scala. Class can have any name that you want, either alphabetic or symbolic. And so you get an instance of squiggle, and you can think of squiggle as a pair. It's just a pair with a slightly different syntax that's a little bit more convenient for us. They could have used pairs, but then the syntax would have looked ugly with a bunch of parentheses. We already have too many parentheses. So that's what it does. So it gives you basically a pair of the two results. So for example, when we look at the simple language parser from the previous slide, and we ask it to parse the expression 3 minus 4 times 5, then here is the result that we get. We get this really ugly looking thing that I don't even want to read to you with a whole bunch of squiggles. It's a little bit easier to read. Yeah, first of all, right now this thing looks scary, and we will never do this after this lecture. In the next lecture, you will see how to transform the things as they are parsed on the fly into something more useful. So this is just the default result. But you'll see in the lab today, even with this thing, we can do something with it. So you can see a little bit better what it does if you take out the nones and the sums, and then it looks kind of like what you see here. And you see there's something remarkable. You see that it has gotten this idea that the 4 and the 5 are close, they're related with each other. So the multiplication binds stronger than the subtraction. It's gotten it from the way that the grammar was set up, that is the case. And so again, if you look at the tree that was built up on the whiteboard, that you can also see that the multiplication somehow clusters the 4 and the 5, its arguments together. And so that means that the grammar was the right one. I could have chosen a different grammar to correctly parse all arithmetic expressions. Instead of parsing, having this two-layer thing where I have the exponent determine the factor, I could have tossed all 4 operators into a single rule, but then the parse tree would not have been as useful. Then in the parsing process, I would not have gotten the operator precedence. So it takes some skill to build the grammars that actually are useful for the parsing process. Okay, so a quick thing about the option type. So an option is something that expresses that a value could be present or not. I'll give you an example from the standard Scala library. The find method for lists and for sequences takes a predicate, and then it gives you the first element of the list that matches the predicate. Now, of course, it could happen here, we're matching whether there's an even element in a list of integers. It could happen that there is none. Maybe the list was empty. Maybe the list only contained odd numbers. In that case, what should find return? Null, right? If it was Java, you would return null. But we can't return null because this is a list, the result has to be an integer. Well, an int in Scala is not nullable. An int is never null. Now in Java, of course, it would then return, you would have to use an integer wrapper, and an integer wrapper is either something or null, but actually it is a real hassle that those wrapper types, integer, Boolean with uppercase letters in Java, that they are nullable. Because you can get genuine errors out of it, right? You then try to put them back into an int or something, and then if they were null, you get a null pointer error. So those are actually fertile reasons for getting null pointer exceptions in Java. And so this entire idea of saying that when you have a type foo, that it means a foo or null, in many cases makes no sense. What the Scala library does is they really stay away from anything that might be null. And you may remember a few lectures ago I said, have this thing return null. It wasn't a homework, right? Even though that's not what we would normally do in Scala. So what we do in Scala is anytime that something could be present or not, we return an option. An option is a class, a generic class, that describes either something or nothing. So the find function, or the find method, returns an option of int that either holds the integer or is an indication that there was no solution. There's any number of things you can do with an option. It has probably 300 methods. Look it up in Scala doc. It has a lot of methods because you can consider an option as a sequence, a very short sequence of either length 0 or length 1. And every other function that you can do with a sequence, you can do with an option as well. But the easiest thing to do with an option is to use a match statement like the one that we've seen on Monday. So when we want to analyze what this result is, we just do match. Say there's two cases for an option. It's either sum of x, where then x is the actual answer, or it is none. So we have a case sum of x, and in that case x is bound to the thing that sticks inside the option, and we can do here, I'm just printing it. Or if it's none, then there's of course nothing inside, there's nothing to bind, and then I do my alternate action. So as a first rule of thumb, when you get an option, you can always use the match and do it like that. Later on, we may find some other cases where there's a more elegant way of dealing with that, and that's where the monadic nature of the option would come in. But right now, we're just going to do it very pedestrian. Okay, so anytime that something is absent or present, then the option would be there. All right, so now I have a lab, and that we want to spend a fair amount of time on because it was actually more confusing to the people in the other section than I thought. And so I really want you to bang your head against it, and then we'll talk about it in detail. So the first thing, or rather the zero thing that you need to do for this lab is you need to set up an SBT project that contains the library for parser combinators. That library is no longer a part of standard Scala, and you have to add it in. So make the SBT project in the usual way, as shown here in the first several lines. And then you need to look inside build.sbt, and you'll find that the standard template, that Scala C.G8 thing that we've been using, that has put in a dependency on Scala test, but we need to have a second dependency on the combinator parsers. So you can rip this line out and replace it with the second. The first time you do that, you probably want to do it with a text editor. One of your fellow students in the first section has figured out that the sed command does the thing without a text editor, so you may want to try that out as well. And that'll work too. And if someone really wants to be a hero, it's got to be possible to figure out this iterator mechanism. I've Googled it a little bit. And there is a way of making these templates. If someone were to make a CS152 template and put it on GitHub, then we wouldn't have to do any of this nonsense anymore. And so you would earn yourselves eternal gratitude. So if you have nothing better to do over the weekend, that would be a great little project. Now, when you use Eclipse, then you need to make the Eclipse project out of SBT in the usual way by adding this plugin thingo and running SBT Eclipse. And at that point, you import your Eclipse project into Eclipse, and SBT is done. If you use IntelliJ, you can skip step 3, and instead you load the SBT project that you've done in steps 1 and 2 into IntelliJ, and you keep on going. I have not found no simpler way of doing this. I've tried to just add the library into IntelliJ by hand, and it was not a fun experience. Yeah?
So I was going to comment on that. So IntelliJ doesn't use SBT directly. In fact, it only supports importing SBT
That's correct.
projects. So in our case, if we use IntelliJ, because I can't invoke SBT from
Yeah, you really want to be able to invoke SBT from the command line, or otherwise you have to rediscover how to do these things in IntelliJ.
I think you mentioned that it should be included, but then it's not.
No, it's a separate. You have to download it. You have to set your path to it.
Oh, okay.
Yeah, it's not an automatic. Probably somewhere in the guts of IntelliJ there is an installation of SBT.
They don't
But
that.
yeah, so go back to lesson 2 or so where it says to acquire SBT, and then put it on your path. Yeah, without being able to run SBT, it's just not worth trying to figure out because there's some random sequence of mouse clicks that gives it to you, and it's going to be too difficult to document.
Random sequence.
Well, okay, it's not random, yeah. Yeah. Okay, so the steps themselves are fairly straightforward. It really is mostly a copy and paste kind of thing. But like I said, people found it surprisingly difficult. So give it a whirl, and then in 20 minutes or so, we'll talk about it.